Thank you. So last time we were looking at surface cluster algebras, and for each cluster variable, we were concerned in getting the expansion of that variable in terms of the initial cluster variables. And to do that, we were looking at t-paths. And today, we'll use that way of thinking coupled with a bunch of other results to find linear bases of the underlying cluster algebra. Well, yeah, the cluster algebra. And so maybe it's helpful to recall other things we've seen this week. So we've seen that in finite type cluster algebras, the cluster monomials form a basis. And outside of finite type, although the cluster monomials are linearly independent, they don't span the cluster algebra. And so I suppose it's been a bit of a hot topic in terms of finding some natural way to extend this set of cluster monomials into some bases. And so this has been done in a bunch of ways in a lot of different settings, and obviously I'll look at this in the case of surfaces. So let's just kind of set out the problem again. So here we have that cluster variables. We know that they correspond to arcs on our surface. The clusters are in correspondence to triangulations. And what does that mean about the cluster monomials? Well, it means they correspond to finite collections, or actually just collections. They always will be for finite collections of non-intersecting arcs. Right, and in this collection, arcs can appear more than once, right? And so when we're not in finite type, so when we're not on the polygon, we need to realize which elements are going to come from our surface that are going to extend the cluster monomials, that are kind of going to extend this collection of non-intersecting arcs, right? Extend our arcs. So our proposed solution is going to be the following set. And it's going to consist of finite collections of mutually non-intersecting arcs and simple closed curves. Okay. Oh, okay. I mean, the stories continue as it was before. So this is for unpunctured surfaces. Yes. Okay. Okay, so in this definition, like we mentioned here, I should say finite the same curve in a given element in this class can appear more than once, right? So the same curve in such a collection can appear multiple times. Right, this is not like a triangulation. And so from here we can see what our kind of substitute candidates are going to be. It's going to be these simple closed curves. And we'll try and spit out a basis from here. So B circ is defined to be the elements corresponding to products of the curves in such a collection. Right. And so at this point, I mean, I'm cheating a little bit because right now, the only connection we know are that the cluster variables are in correspondence to arcs. So definitely we understand what this variable means when we're dealing with an arc, but what does it mean when we're dealing with a simple closed curve? And so you can kind of understand that in two ways. So if you're familiar with lambda lengths, then this this variable corresponding to a one-sided closed curve is going to be the lambda length. And if you're not familiar with that, then we won't be able to define this at this moment, but it's going to come kind of from our consideration of t-paths, right? Before we knew this link between the cluster variable and some Laurent polynomial that a t-path was spitting out. And so kind of we can artificially define that variable in that way as well, right? We can have some notion of t-path for these one-sided closed curve and spit out some Laurent polynomial, and then that's what the variable will be in that case, right? But we'll come to that in a bit. But if you're familiar with lambda lengths, then that's what that means, okay? And the two things coincide, of course. Okay. So what should we note at this point, just to kind of solidify the idea? Well, when our unpunctured surface is a polygon, then what is this set? Well, it's just exactly the cluster monomials. It's only when we go outside of the n+3 that we get kind of additional elements, and those are the additional elements that we actually do need if we want to succeed in getting a basis. Okay. So what do we want of this proposed set? Well, we want to show, of course, so okay, if we want to show that this set is a linear basis, of the cluster algebra, over the coefficient ring, then okay, any undergrad student will be able to tell you that B circ needs to span the cluster algebra. needs to be linearly independent. And then the final kind of subtle thing is that, of course, we need that these elements belong to the cluster algebra. So we need that B circ is contained in the cluster algebra. Okay. So we'll tackle these problems one by one. And so the first thing is we need to show spanning. And the idea for this is to use the notion of smoothing of intersections. So starting with some kind of bunch of intersecting curves, and then eventually split them into collections which don't intersect anymore. So take gamma 1 and gamma 2 to be curves intersecting at some point, P. And then we define the smoothing at P by the following picture. So the smoothing of gamma 1 and gamma 2 at P is defined by looking at the following picture. So here we have gamma, and here we have gamma 2. Here's a point of intersection. And so we split this collection of curves into two different ones. By resolving the intersection in the two possible ways we could resolve it. Okay. So we could resolve it this way, or we could resolve it this way. And, okay, so if this belongs to a class of curves C, then we'll define this as C plus and this as C minus. Okay. So let's just give an example. And okay, before we do an example, one thing to note is it's possible, like I do allow gamma 1 to equal gamma 2, right? We can apply this on self-intersections, okay? And so we're allowed to smooth on self-intersections. So now we can look at an example. Take two simple closed curves. There are two intersection points, and so to smooth we can just pick one of them. So let's pick this to be our P. And so what is smoothing in this case? Well, if we resolve it this way, we get this guy. So this is C plus. And if we resolve it the other way, we get this. Okay. And okay, so one thing to note from this procedure is that C plus and C minus might have kind of different cardinality of arcs, right? I mean, in our example, we had two arcs, two curves here, and then it's split into to one arc here and one arc here, and it can also go the other way around. Why we could have just maybe one arc here, and it could self-intersection, and it could split into two and something else, right? But the key thing to note is that we have reduced the number of intersections, right? Say there were k intersections in C, there would be fewer than k in C+, and there would be fewer than k in C-, right? After this smoothing procedure. Okay. And so this is going to be the idea of what we do. We start with a bunch of intersecting curves, and we continuously apply smoothing, so we're left with a bunch of collections of curves in which none of them we have intersections. Okay? Yeah? Oh, it's just notation. Yeah, there's no, I could have easily replaced plus. I mean, yeah, because of course you can like kind of twist your surface. Yeah, it has no meaning, plus or minus. Yes? No, I mean, yeah, you did have a label on them before, but there's no labeling on them anymore, right? There's no consistent labeling. Okay, I mean, we were just using this notation of gamma 1 and gamma 2 to talk about the intersection point between them, but afterwards, I mean, because of the, I mean, like I mentioned, in terms of the cardinalities can change, and so there's no consistent way to keep talking about gamma 1 and gamma 2, yeah. I mean, they make no sense over here, okay? Okay. So this is on a very topological level, but we would like to kind of explain these moves in terms of the variables, right? And so this was done by Musiker and Williams. In 2011, which says that when we're in a cluster algebra with principal coefficients, we have the following. So this variable corresponding to a class of curves C is equal to y1 xc plus y2 x c minus. So this is called the Skene relation. And okay, so we know what xc plus and xc minus are. What are these y1 and y2s? Well, these are just monomials in the coefficient variables. Okay, and so once we know this, then actually we're done, right? In terms of proving that, that this B-circ spans the cluster algebra. Okay, so why are we done? Well, we know by definition that the cluster algebra is generated by the cluster variables. So the variables associated to the arcs. Okay. So to prove that this basis spans the cluster algebra, we just need to consider a collection of arcs that, okay, maybe they intersect a lot. And we need to realize that that associated product can be written in terms of the basis elements, right? But then the scheme relations give us exactly this. So since for any collection of intersecting arcs, we have, so arcs for any collection C, we have xc equals the sum over the coefficient ring of elements of B circ by repeated application of smoothing and scheme relations. So repeated application of scheme and smoothing shows that B circ spans the cluster algebra. Okay. Right, so number one is done, and we would need to move on to linear independence. And this is by far the kind of most involved part of the story. And everything we do from now on will be trying to latch onto this proposition that I'm going to write down and kind of fit it into this form. So what is the proposition? Well, the proposition is by Musiker Schifflo-Willians. Again in 11. And it gives a bunch of conditions that will ensure linear independence. So what is the first thing that is required? Well, we're asked to have an M by N extended exchange matrix. So B tilde be an M by N exchange matrix. And the condition we ask is that the columns be linearly independent. Okay. So that's the first condition. And then we're concerned with a very specific class of elements in the cluster algebra. So we're asking for a set U. And like I said, it's a set of elements in the corresponding cluster algebra. Of the following form. So we have some leading term xg, and okay, I'll write it down and then explain all of the terminology in a moment. We have some leading term and then a sum of other terms. Okay, so what do the things mean in this form? Well, as Piaghi mentioned, it's kind of standard to write xg where x is extended cluster. So let's say x of A is defined to be x1 times x2 to the power of xm. So it's the extended cluster, and A is some m-tuple. So the exponent of x1 is a1, the exponent of x2 is a2, and the exponent of xm is am. So, okay, let me say so. Where x is the extended cluster and A is some m-tuple. Okay, and so in this sum, what is lambda h? Well, lambda h is just some integer. And, okay, more importantly, what is this sum over, right? Well, h is again in Zm, but it's a very specific thing. It's a non-negative linear combination of the columns in B tilde, yes? Lambda h is what I've defined here, and it's just some integer. Does that answer your question? Yeah. Right, and the sum is over non-negative linear combinations of columns in our extended exchange matrix. Right, so this is one of the conditions, and then what is the final thing? Well, finally, we suppose that we have a certain uniqueness property of this leading term. So we suppose that for any two elements of this set U, so with any two elements with associated leading term G and G prime, that we have a certain distinctness, and it's actually, the uniqueness is in terms of the first n of the exponents are different, right? Well, at least one of the first n in the two of them are different. So the condition is that for any of those two elements, we have that G1 up to Gn is different than G1 prime up to Gn prime. Okay? And the claim is that if we have all of these things, then the set of elements U are linearly independent. So I guess I can fit it in at the bottom. Then the elements of U are linearly independent. Mm-hmm. You can cancel what, sorry? Non-negative, do I allow H to be 0? No, I don't allow H to be 0. Yeah, okay. I mean, at least one of them has to be positive. Yeah, exactly. There has to be something in the sum, right? We don't take non-empty sum. Yeah, exactly. Yeah. Okay. Right, okay. So how would you prove such a thing? Well, it's actually very simple. So, okay, so our sum, okay, so first, okay, how would we prove it, right? So we put a partial ordering on z to the m. Zm, how? Well, by saying that u is less than v if and only if v equals u plus non-negative linear combination. Non-negative linear combination of columns in V tilde. Okay, so this would give us a partial order. And then, obviously, with respect to this partial order, this term here is a leading term, right, with respect to this partial order. So note each kind of respective xg of elements in U is the leading term. With respect to the partial order. Okay, and then this distinctness property will ensure that this collection, therefore, is linear independent over our coefficient ring. Distinctness of the leading terms implies linear independence over the coefficient ring. Okay. Just because if we took any collection of U, there would be at least kind of one minimal term that we wouldn't be able to get rid of without the coefficient being 0. And, okay. Right. So, as I mentioned, everything we do will revolve around this proposition. And so how are we going to fit our kind of approach into this setting? Well, the first thing we need is linear independence of columns. Well, to this, we can choose principal coefficients. So, okay, to be precise, what is B tilde in this case? It's of the following form, right? We have our exchange matrix on top, and then the identity matrix on bottom. And of course, such a matrix has linear independent columns. Then, to get it in this form, satisfying these conditions, we'll use snake graphs, which are very similar to what we've seen already in terms of t-paths. And then the final condition of distinctness, we will use the notion of g-vector. This is just to keep in mind what our approach will be. Okay, so we've mentioned snake graphs, so what are they? Well, we'll define this now. So it's very similar to what we have seen before in terms of we're going to fix the triangulation. Fix the triangulation T and a directed arc. Directed arc alpha. Right, and I mean, we're kind of using the notation that we've seen before in terms of ordering these intersection points, naming them P1 up to PD if there are D intersections. Okay. So what is this method of constructing the snake graph? Well, the first step is consider the quadrilateral on our surface containing the intersection point P1, right? The first intersection point along this directed arc alpha with the triangulation T. So take quadrilateral containing P1. And what are we going to do with this quadrilateral? Well, we're going to rotate it to look like the following. Okay. So it's either going to look like one of the following pictures. So the first thing is we rotate it. So I mean, the arc that we're intersecting is the diagonal of this quadrilateral, and it's rotated like this. And of course, there are two ways to do that. But we orientate it in such a way that our arc starts at this vertex, and then it's going to either leave through this edge, or it's going to leave through this edge. Okay? And so P1 is the first intersection point, so it's here. Okay. So this is the first step, and this will be our first tile of the snake graph. Okay. So such a quadrilateral is called a tile. And what is the second? Well, now we look at the second intersection point. And we look at that quadrilateral, but we don't quite look at that quadrilateral, we look at its mirror image. And we glue the mirror image of that quadrilateral to this first tile. Containing P2 to the first tile. So this tile up here. Okay. And we glue it along either the north or the east edge. Okay. I mean, there's obviously a repeat in terms of this tile, and so kind of when we see the same arc, then we glue along that arc, right? And we'll be gluing along either the north or the east. I mean, I'll write it down, and then we can go through an example, and hopefully then it's more clear. Okay. And this procedure, I mean, we just carry on, and we keep on alternating between looking at the actual quadrilateral containing the next intersection point, and then the mirror image of the quadrilateral containing the next intersection point. Okay, so we carry on. Okay, and so what will be the 2kth plus 1 step? Well, glue quadrilateral containing P2k plus 1 to the tile before, so the 2kth tile. And then, of course, in the next step, we need to glue the mirror image. The mirror image of the quadrilateral containing P2k plus 2. To the tile before, so the P2k plus 1th tile. Okay. And then, okay, this process obviously terminates when we're out of intersection points. And once we've finished, then in all of these tiles, then we delete the diagonals. So, of course, by the end of it, we'll just be left with a kind of bunch of squares all glued together. Okay. So maybe I can write the example next to the definition. Okay, so let's look at the 6gon. And we, of course, need to pick a triangulation. And we need to pick our arc alpha. Our arc alpha. And we need to put some orientation on it. So let's orientate it this way. And just to make it easier to understand what's going on, let's also label all of the arcs. The boundary ones from A to F. And the interior from X to Z. Okay. So the first step in obtaining the snake graph is we need to look at these intersection points, and we need to take the quadrilateral containing P1. So we're looking at this one first. And okay, the first step is we need to orientate it in one of these two ways. And actually, we'll see that the orientation that we're going to have is this second tile here. Yeah, first section is P1, and so we're looking at the quadrilateral containing P1. This is the yellow tile on the surface. And what are the boundaries? What are the kind of edges of this tile? Well, it's A, Y, E, and F. Okay, so that's our first tile. And now we need the second tile, right? So the second tile is the one containing P2. So it's this one. Okay, and so let me just draw this tile out here. Okay. So what does it look like? It has X, Z, D, and E, I guess. Okay. But we were told not to look at this tile, we were told to look at its mirror image, yes? So we need to take the mirror image. Which is D, Z, X, and E. Okay, and then we need to glue this picture to this picture on either the north or east, right? And so how can we do this? Well, this is E and this is E, so we need to glue them together, yes? This is the picture we have. So this interior diagonal is X, and this interior diagonal is Y. And so it's D, it's DZ and X. This was our blue tile. And then finally, we just need to look at the final intersection point, P3. Let's color this quadrilateral green. And, okay, we need to glue it to either the north or east edge. And, of course, the only way we can do that is here, D. So we need to glue this. And so our kind of end product is the following. So sides dy, B, and C. And okay, so we've run out of marked points, and so the final thing we need to do is delete the diagonals, right? Right. So this would be our snake graph, and we'll use some notation. So the snake graph of this guy, so the snake graph of alpha with respect to the initial triangulation is S gamma t. Okay. Yeah? I mean, we can carry on drawing the curve. What do you mean we don't care about the curve anymore? Oh no, I mean, we don't keep this was really just to kind of convince people which way we were going to look around, but no, I mean, it kind of makes sense to draw it, and we can draw it. So here, what we'll get this, and so here was y, and then we repeated, we'll get this. Yes. Well, so we definitely don't get it might seem like we get a choice, but it's uniquely determined in terms of we just glue it the way that we could, right? So exactly with respect to the labeling, exactly of the arc, yeah, for sure. Okay. Is this clear? Okay. Okay. So yeah, okay. Here was our surface, here was our arc, and this is the snake graph it spits out. So far, this only applies to arcs. I will explain what one would do when it comes to one-sided closed curves. I mean, the general idea is that, well, okay, you have a closed curve, and so you have kind of, well, a bunch of intersection points, but you come back to the same spot, and you have a. So you would kind of draw an extra tile that is this tile repeated, and then this would tell you how to glue this, the north or east edge to this tile. And so you wouldn't end up with a kind of snake graph. You'd end up with a loop, right? A cylinder or a Mobius strip, right? I mean, this is the general idea. I think I will write it in a moment. But yeah, okay. At the moment, this is just snake graphs are for arcs, and band graphs are for one-sided closed curves. For closed curves, sorry. Okay. So the whole point is to link this back to t-paths and kind of read off the expansion formulas of this snake graph, which turn out to be a little bit easier to deal with when you're dealing with coefficients, right? You can say a little bit more about them, yes? Sorry? Oh, the mirror, yeah, I mean, well, I mean, we take the mirror image just so we get something that kind of is going, either side or up. And if we did it the other way around, then I mean, I guess we would loop back. But I mean, in reality, we do it because it works. And maybe I'm not allowed to. Maybe I can't say anything intelligent about why we're taking the mirror image. Yeah. Okay. Mm-hmm. Yeah, because on odd tiles, we have the actual quadrilateral on the surface, and on the even tiles, we have the mirror image. Right, so it oscillates between tile on the surface, mirror image of tile on surface, yes? Yeah, so I mean, you just have to remember that we have kind of repeated area, like this is on our surface and this is identical to this, but it's just the mirror image, right? And so here, I mean, we've gone on our surface and we've popped out here, yes? I mean, this is just extra information. Are you saying you would have wanted to see an arc like this and then an arc like this and sorry? I mean, all I'm doing there is literally, this is part of the surface, and I'm just drawing what's on the surface on this tile, right? This is just a part of the surface, and that's what locally this looks like on the surface. Does that make sense? Okay. Okay. Right, so how are we going to link this, this snake graph to the t-paths? To do this, we have the notion of perfect matchings. So what is a perfect matching of, more generally, just a graph? So a perfect matching of a graph is a subset of edges of that graph subset of edges such that every vertex of the graph appears in this set of edges. And moreover, every vertex is contained in precisely one of these edges. Okay. So we have the following proposition due to Musiker and Schifflo, which links the t-paths and perfect matchings of the snake graph. So, okay, we have the following bijection. So the complete t-paths of alpha are in bijection with the perfect matchings of the snake graph. And okay, so maybe I should actually just give a definition of perfect matching. We could take something like this. Every vertex is contained in precisely one of these edges. Okay. And okay, actually I could give an example underneath, because this correspondence is explicit. So, well, okay, I'll write the kind of the vague way one says this, and then we can actually give an example. So does this timer go off slightly early then? How long's left? 15? Okay, awesome. Yeah, thanks. Right, okay, so what is going on? Well, let's suppose we have some t-path. How do we get to a perfect matching? Well, you draw this t-path on your snake graph, and then you just delete the diagonals. Okay? Or you draw it on the snake graph before you've deleted the diagonals, and then you delete the diagonals, and then you're left with a bunch of edges, and this turns out to be a perfect matching. Okay, and going the other way, if you were to start with a perfect matching, you would add in the diagonals. Then you would start at this bottom corner to get a path. And then you draw that path on your surface, and this is a complete t-path. Add in the diagonals. To create induced path on your surface. Right. So an example. Okay, so remember our arc is going from this vertex to this vertex and orientated as such. So here we can go along one, we can come along down this edge. Remember, even arcs need to intersect the arc alpha, and we can go 3, 4, because even arcs have to intersect. And we can go 5. And because even arcs have to intersect, we have to go back along that. And then we end with the top one being 7, the 7th arc in our path. Okay. And, right, okay, we can draw this on this guy over here. It turns out the way we're drawing is like this. And okay, after deleting those diagonals, we're left with the perfect matching that I just drew. Okay, and so relating this back to expansion formulas. we know the expansion formula of this cluster variable corresponding to alpha is written in the following way, where zeta is over all complete t-paths of alpha. And let's just draw a sum over here. So P, perfect matchings of the snake graph, and we'll say XP. And so where is XP? Like, how is it defined? Well, it's defined as the product of all variables corresponding to the edges in your snake graph. So delta in P, X delta. Okay. So I've drawn this, and we want this to be equal, but as I've written it, it's not equal there. So why? Well, remember what is this quantity? It's taking the product of the odd arcs and dividing by the evens, right? And so in this perfect matching, we had some t-path, but we deleted all of the even arcs, right? And what were the even arcs? They were exactly the crossing points of alpha. So if we want these to match, we would just divide by the crossing points of t and alpha, right? The crossing monomial. And hopefully, okay, from what I've just said, hopefully it's clear how I've just defined that crossing monomial. Okay, so I'll finish by describing how one can add coefficients into this picture. We know how to add coefficients into here, and so of course, if we wanted to add coefficients to this side, we could just take our snake graph, use this bijection to go back onto the surface, and read off gamma-orientated arcs by doing that. But there's a slightly quicker way, which just requires you to, in some sense, just draw the t-path on your snake graph rather than quotienting down to the actual surface itself. So the final thing I say today is just the way one would read off principal coefficients from the snake graphs. Right, so for t-paths, as I just said, we know that x of alpha is equal to the sum over the complete t-paths. Where y, zeta, is defined to be the product over all alpha-oriented arcs. And so let's just look at this snake graph for a second. We know that in this first tile, when will this even arc, so aka the diagonal, when will it be alpha-oriented? Well, it's alpha-oriented if it's going in a cycle, right? So if it's oriented downwards, and the story in the even tiles, well, it's not the same because we've took the mirror image, right? So instead of being alpha-oriented when it's going down, the diagonal is alpha-oriented when it's going up. Okay? So the way that one can read off the coefficients here is the following. Remark. So gamma I2k is alpha oriented if and only if tile is odd, and when you draw the t-path on your snake graph, the tile is oriented downwards. And when it's even, it's alpha-orientated if and only if it's oriented upwards. Okay, so today that is all I will say. And the story, kind of how it continues, well, for one, I mean, we've only been dealing with snake graphs, so we've only been dealing with arcs, and I'll mention kind of quickly what the story is when you look at closed curves, which is, I mean, almost the same. And from then, we just want to know kind of how to move between these perfect matchings. I mean, this is the reason why we looked at these snake graphs, because the story about how we move between the perfect matchings can be described very nicely, and then this is how we will latch on to getting the cluster variable, the variables corresponding to the curves in this form, right? With we had the leading term, and then the other exponents were sums of. And it turns out when we kind of do these, when we move between perfect matchings, and we just do one of these moves, then it just adds a column in our extended exchange matrix. And kind of this is the general idea that will be explained last time. But yeah, for today, this is all I'll say.